Okay, welcome back to Troubleshooting EIGRP. This is part 2 of the 4 theory presentations. So in this one we'll be looking at troubleshooting the IP routes within EIGRP, and we'll be looking at how that routing information is exchanged after the neighbour adjacencies have been formed, how the topologies are formed, why they may be missing information, and let's get started. So the common areas that cause issues with EIGRP is missing or bad network commands. Now, if you cast your mind back, under the EIGRP process, we need to identify the networks that are actively participating within the process, and we do this via network commands. Next item there is source information. Now, there's various reasons why we may get our EIGRP route dropped, because EIGRP is not the only protocol out there, and there may be a better path or something like that around through another protocol or something like that. Route filtering, this is a big one where we will lose networks from our routing table. If you remember our lab session on Stub networks, you'll understand if somebody puts a Stub router in the wrong place, it really messes our routing tables. Interfaces need to be active within the EIGRP process. So if a interface is shut down for whatever reason, that interface is no longer advertised as an active interface, so the route becomes invalid. And then we've got the lovely loop prevention split horizon. So if you cast your mind back, we don't send advertisements out the same physical interface that the updates were received on. So, how do we check our network commands? Well, first off, we can use the lovely show IP EIGRP interfaces. If we're not getting peer relationships occurring, chances are that we have an incorrect network statement within the routing process. It's not the only reason why we may be missing peer, but it's one of the good ones. So the other way we can look at our information is using the show IP route and listing the route that we want to look at. Now, some things to remember when we go through and look at our routing tables. Remember, EIGRP learns these routes from their own directly connected networks and the routes being advertised from other devices. So if they're coming from a EIGRP source, they'll have an administrative distance of 90, or if they've been injected externally to the routing process, they'll have an administrative distance of 170 as they're an external source. So just with that, our internally learnt routes are more trusted than the externally learnt ones. And then you have the possibility of having other routing to calls running as well. So when we're talking about better sources of information, one of the things we need to look at is the administrative distance, because remember, that's the first deciding factor on how trustworthy a source is. So in this example here, we have a suboptimal path being formed because the OSPF administrative distance is higher than EIGRP's. So instead of taking the 10 gigabyte link directly between our routers here, because it's under OSPF, it's not as trusted as the less efficient route through EIGRP, because of the administrative distance is 90 compared to 110. So what we need to do is look at our topologies and make adjustments to our administrative distance for certain routes, and we can adjust that. Now, we looked at distribution lists using ACLs and IP prefix lists. We didn't look into route maps, but they're just another way of filtering your updates and selectively removing or excluding networks from those updates going to and from devices. So if we have a filter in place, it may be adversely affecting our routing tables. So if we look under Show IP Protocols, and we'll see whether there's been a filter applied, outgoing and incoming. And in this example here, we can see that on our gigabit 10 interface, we have a filter by the name of 10. Okay, so we can look and we can find a distribution list 10 being applied in the running config under the router EIGRP configuration settings. So you would then go in and find the other elements associated with that distribution list and see what impact that filter has on your routing tables. So what routes are allowed, which ones are denied. You may need to adjust it to get connectivity. Stub networks, I hope you remember the example and the demonstration in the lab of how a incorrectly placed stub router can adversely affect the behavior of updates. So with a route going down, the router will send out queries to other devices trying to get a secondary path back to that lost network. Now, when you hit a stub router, like in this here, router 2 knows not to send a request, a query, to the stub because it's only got one path and its routes are its routes that are advertised. There's no other repathing available to it as it's only one entry in and out. So using stub commands, make sure you put it in a device that has only one connection to the rest of the network. So it is an actual stub. Alright? So there's no way of wrapping back in and around to another destination. So when we are using the old hub and spoke feature and we have stub connections, it can come very useful because we can limit the querying traffic across WAN interfaces here going to these stub networks, because there's only one possible connection coming from these devices back into the rest of the network, and as they are advertising all of their downstream, because it's all connected to this device, that router 1 in this demonstration knows not to contact them because there's no possible loop back into the rest of the network. So understanding how stub configurations work, you'll be able to troubleshoot the associated route population through the rest of the network. And how do we confirm something's configured as a stub router? Under IP protocols, we'll get a stub listing, and when we do our show IP EIGRP neighbors details, we'll get a stub peer advertising and the note saying queries are being suppressed. So it's pretty clear if you use the correct commands what those modes are. This relates to our earlier comment that the interface needs to be up and up. So the interface is down, you're not going to get any neighbor relationships forming with the devices. And if it's a participating route that may be a passive interface anyway, if it gets shut down, the device knows it is not active, so it's not going to advertise that network that's connected to that interface in its updates, because it's no longer active, so therefore the routes are invalid and it removes it. Split horizon is our loop protection mechanism where we will not send updates out of the interface the update was received on. So in the example here, router 2 sends its update through and it'll be updated on router 1 and router 4, but not router 3, because it can't send it out of the interface that it received it on. So therefore, as it's a shared physical interface, it cannot send that update to router 3. So when we're looking at the show IP interface and whichever one, so in this example it's a tunnel interface, we can see that split horizon is enabled, so it's blocking that retransmission of the update through that hub interface. So to get ourselves around this, we disable split horizon on that physical interface because it's acting as a hub and spoke with the no IP split horizon, and then specify the protocol and the autonomous system number to turn it off. Be very careful doing this because you can generate routing loops by turning off split horizon. So be sure of your topology before you disable split horizon. Okay, so that's another little short chapter for us, and until next time, bye for now.